Hi, this is my attempt at the video presentation in the computer vision subject at NTNU. My name is Thomas Friman Koden, and I'm a member of Group 18. So, my goal is to give a more intuitive introduction to the Fourier transform and try to make it a bit easier to see the connection between the formula and the result. And I didn't really see someone presenting it this way on the web, so hopefully it works out. Okay, so the Fourier transform is, in the continuous case, the two-dimensional one is like this, and the discrete one is like this. Well, this is all well, and you've probably seen these formulas and you can use them, but well, this is Greek to most non-mathematicians. So, well, but what do these give us? Or, well, why can we do this is what I've written, but yeah. All periodic signals can be described as a sum of signs, as you know from the one-dimensional Fourier transform. You probably know this very well. And the Fourier transform shows the frequency of these signs, right? Well, the same actually goes in the two-dimensional case. But in this case, the signs are stripes of varying frequency and going in different directions. And you can just like layer and layer and layer these stripes, and in the end you'll end up with some kind of image, or two-dimensional periodic signals. Because images can be seen as a kind of two-dimensional periodic signals. You can just repeat them in all infinity in all directions, and then you have a periodic signal. And, well, then an image can be described by its frequency components. Well, that's great. So, when you do the Fourier transform, you end up with a two-dimensional complex array. And we usually split this into the phase, the angle of the complex number, and the spectrum, the magnitude. And as the book shows really well in an example, the phase mostly contains the shape information, and the spectrum contains mostly intensity information. This woman here, in this case, her spectrum is used together with the face of a rectangle, and well, in this case you mostly end up with this large DC component, which comes from the fact that she's pretty white. But here you have the face of a woman together with the spectrum of a rectangle, and here you can clearly see the outline of the woman. So then a bit about the human readability of the Fourier transform, or the phase and the spectrum. Well, the phase usually comes across as noise, and is not really that human readable. However, the spectrum does have human readable features, like the direction of borders, which is the most obvious one. And, well, this is shown very well in the following animation that I've made. Oh, and excuse, there's a lot of artifacts in the Fourier transform. I think they come from Photoshop's anti-aliasing. Okay, and then over to the next part. And also, like, if you have periodic elements in your image, it's possible to see the frequency information of this in the spectrum. Well, obviously, as this is a kind of frequency, or, well, yeah, frequency transform. So, well, this is shown in the following animation, where you can see the frequency components increase as the amount of radial stripes also increase. So that means that when you get more stripes, you will see that the spectrum will like zoom in a sense. Oh, and there's also a lot of artifacts in this one due to the fact that gradients in Photoshop have a lot of banding, which creates a lot of extra frequencies, and also the anti-aliasing thing and everything. Okay, Go animation. Okay, well, thank you. That's everything I had to say. Hope you enjoyed my presentation. Thank you.